Hello friends, continuing with the video regarding orbits, we are going to talk about how we can reach from the Earth one orbit. From a theoretical point of view, we have several options. First one, we can consider that we launch the rocket vertically, and then once we reach the orbit, we turn in horizontal in order to get the tangential movement. Then a second option in which we launch the rocket vertically too, but then gradually we are turning into horizontal in order to reach the orbit in a proper way. Then a third option that could be, let's imagine, more efficient, as we launch the rocket horizontally in order to avoid the vertical component, and seems to be much more efficient. But if we remember, we have the 100 kilometers thickness of the atmosphere, and in this third option we are going to travel quite a lot of time with high friction with the atmosphere, and that means that it's going to be anti-economical, let's say too expensive. So we dismiss this third option, and then let's focus on the first option. The first option, in general, if we move from one point to another in the space, the straight movement, linear movement, is not so. Let's make some considerations. Let's imagine that the moon is not moving while we are traveling from the Earth to the moon. Let's consider that it's fixed. Earth and moon are fixed during the 3 days that is needed to reach the moon. If we consider, let's say, the data from the Apollo 11. So in this linear movement, the use of fuel is going to be quite higher. We are going to see that in real, in the Apollo 11, we could see that they make use of the orbit before they speed up from 27,000 kilometers per hour to 45,000 kilometers per hour, which allows them to reduce the mistake in the trajectory. Much more than in a linear movement, when during the launch and pass through the atmosphere, there are quite much more mistake in the trajectory. And to correct this once we are in the space is much more expensive, as we have to use much more fuel. Another point is that as we spend much more fuel in a linear trajectory, and also we have possible mistakes in the trajectory higher, we are in a risk of not having enough fuel. And then what happens if we have lack of fuel in a linear movement? Theoretically, let's say that if we are far than 260,000 kilometers from the Earth, then the moon would attract us, and we will hit the surface of the moon at supersonic speed. Whereas if we are less than 260,000 kilometers, we would be attracted by the Earth finally and would hit the surface of the Earth. Not supersonic, because we have the atmosphere, but disintegrated, burned out absolutely. because of the friction with the atmosphere. And then let's talk also about the speed. Once we reach one orbit, we have to maintain this speed. If we are in that orbit physically, but we are at smaller speed than that is needed in this orbit, then we will abandon the orbit. We will be attracted by the Earth until we hit the Earth sooner or later. Whereas if the speed is little higher than the needed in this orbit, then we are going to be moving to another orbits all the time. Why? Because in these outer orbits, the needed speed, the orbital speed, is smaller than in inner orbits. So we are going to be moving far and far and far away, escaping from this. Let's say escaping from the Earth all the time. So how can we move between two orbits, two circular orbits and coplanar? Let's say that there are both orbits contained in the same plane. So if we want to move from A point to a B point in an outer orbit, we have to just increase a little bit the speed. With this, we can force, let's say, one elliptical orbit. So with just increasing a little bit the speed, we abandon the inner circular orbit and then once we reach the final orbit, the outer final orbit, then we have to slow down the speed in order to be stable in that orbit. So we need 2 times, one speeding up and one slowing down. If we use this elliptical orbit to speed corrections, this is called the transfer orbit of Hohmann. And of course, this is also valid to move from an outer orbit to a more inner one. And of course, this is also valid to move from an outer orbit to a more inner one. Now we just remember one concept that we talked in the last video, and is the circular orbit speed. We calculate square root of gravity constant multiplied by the mass of the Earth divided by the distance to the orbit. So with this, we with this speed we keep in that orbit stable. Then if we want to move in an elliptic orbit, then we have to move between the circular orbit and square root of 2 times the circular orbit. That means 1.41 times the circular orbit. So if we are between these two values, we are in an elliptic orbit. So if we are between the circular orbit and 1.41 times this speed, we are in an elliptic speed. And if we are at the same speed of the escape speed, that means that we are in a parabolic orbit. And just to complete all the options, if we are a higher speed of this escape speed, so we are in hyperbolic orbit. So just to put an example, if we are in this 27,000 kilometers per hour in a 400 kilometers height orbit, then if we are 1.41 times this, that means that we are in a parabolic. And if we are between these 27,000 kilometers per hour and 1.41, that means that we are in an elliptic. And if it is 1.41 times 27,000 kilometers per hour, that means that we're in a parabolic. And if it is higher than this, is hyperbolic, and then we are in both parabolic and hyperbolic. We are escaping from the planet. So there is another possibility, is in some case where the inner and the outer orbits are at higher distance than 15.6 times, then it's needed to use another system. Is the bielliptic transference orbit. That means bielliptical is the use of two different elliptic trajectories in order to reach the final point. So we need three, let's say, speed corrections. One first to start one elliptic orbit, then a second one to change to another different elliptic trajectory, and then a final third correction, that is slowing down, if it is the case of an outer orbit, to slow down to a proper speed of that final orbit. So just summarizing also, if we consider now from the point of view of the eccentricity of the different trajectories, we can say that if the eccentricity is 0, we are in a circle trajectory. If it is between 0 and less than 1, is elliptical trajectory. If it is eccentricities equals to 1, is parabolic trajectory. And if it is higher than 1, then we are in a hyperbolic. Let's say that this circular and this elliptical we have talked in this video, and then parabolic and hyperbolic can be really used to speed up satellites, for example, when we are moving quite far away from the solar system and we want to launch at a higher speed. And of course, we have to assume, for example, the Viking has not enough fuel for that purpose, and they use the speed that they can get from the planets of our solar system by means of these hyperbolic and parabolic trajectories. So okay, I hope this video was quite helpful for you, and let's see. Please remember the like and subscribe to the channel. Also remember Patreon if you like, and of course we'll see you very soon in another video. Goodbye.